So, hello everyone, welcome to our channel Only Physics JEE Grad. So, today we will be discussing JEE Advanced PYQs, JEE Advanced PYQs from the chapter Gravitation. This will be the first video, and the topic will be discussing law of gravitation, acceleration due to gravity, Kepler's law, potential, electric, gravitational field. Okay. So there will be another video, the gravitation, which will be based on escape velocity and satellite, and there will be 21 questions from that. But today will be solving question from this topic, and there will be 19 questions. Okay, so let's start with our. Okay, so this will be the first question. Now, what we have here is a spherical gaseous cloud of mass density rho in a free space where r is radial distance from its center. Okay, so we have a spherical gaseous cloud. Okay, it has a density rho r. Now at a distance r it may be changing, or we don't know. The gaseous cloud is made of particle of equal mass m. So all the particles we have here is of mass m about the common center and the same kinetic energy. So they all have same kinetic energy, which is k. Okay. The force acting on the particle is their mutual gravitational force. The rho r is constant in time. So look, it is constant in time, but it may be changing with r. Okay, we don't know about that. The particle number density nr we have to find, which is rho r by m. It is given. So let's say we have a particle here, okay, of this is of mass m. So on this particle, there will be a gravitational force toward the center, right? And there will be centrifugal force, which is mv square by r. Now, the kinetic energy of this particle will be half mv square. Okay. Now let's equate these forces. So Fg will be mv square by r. Now we have to find Fg, gravitational force. Now we know the concept. Look, if I'm talking about the particle here, so the gravitational force on this particle will be due to the particles which are present inside this small sphere. Okay. Now the net force due to these particles which are outside, it will be zero, right? So Fg will be equals to G. Let's say it has a mass capital M. These particle in red, they have the total mass capital M divided by small m, r square divided by r square will be equals to m v square by r. So m will get cancelled, r will get cancelled. So we have g m by r will be equal to v square. This is our first equation. Okay. Now we have to find the like if we get the density with respect to r, then we'll get the answer. Okay. So we know if I take another sphere like this, right? So this will be our integrating element at a distance r. The thickness is dr, right? So what we'll write? So the mass of this integrating element will be dm is equals to rho rho into 4 pi r square dr, right? Okay, now we have to find dm, then we will get our answer. So how we'll find dm? Look, if the kinetic energy is constant, that means the velocity must be constant. Now there is a question which comes into my mind, that if sir v is constant, then the particle here, which is greater than small r, will they have the same kinetic energy? How is it possible? Yes, it will be possible. How? Look, this m is also increasing, right? Okay, so look, m is increasing, r is also increasing, so they will cancel out each other. Okay, so you don't have to worry about it. Mhm. Okay, now we have here m will be equals to v square by g into r. If you partial differentiate it, we'll get dm is equals to v square by g into dr. Let's put it here. So we'll get v square by g into dr will be equal to rho 4 pi r square into dr. So look, dr will get cancelled. We will have density will be v square by g into 4 pi r square. We have to find density in terms of k, so we'll multiply half m and we'll divide half m. So this will be 2, this is g, okay. So this is k upon mg into 2 pi r square. This will be our density. And now if the density we get, so nr will be density by m, so we'll be having k upon m square g 2 pi r square. So this will be our answer. So divide by 2. This is our answer. Okay. Let's move on to our next second question. So we have this. Okay, so these are two questions. So we have a planet of radius capital R, which will be equal to 1 upon 10 of radius of Earth, has the same mass density as Earth. So density of this planet, we can just write it as density of Earth. The scientists dig a well of depth R by 5. So we have a planet and we dig a well right over here of depth R by 5 from the center, of course. Okay, from the surface. So depth will be always from the surface. And lower a wire of same length of lambda. This, okay. If the wire is not touching anywhere, the force applied at the top of the wire by the person holding it in the place. So if this is a wire, look, if I write the free body diagram, so the tension will be here, and from the center of mass, mg will be down. Okay. Now the center of mass will be at a depth r by 5, r by 10, because this hole is r by 5, right? This wire is at the length r by 5, so center of mass will be at r by 10. Now write so let's write the force equation. So we will have T equals to mg. Now we have to find T. For that, if I get g and then I will multiply it by m, we'll get our answer. So let's find g at the center of mass. So it will be at r by 10. So we'll use the formula. G dash will be g of the planet, g of the planet at the surface into 1 minus d by r, right? So g of planet will be g mass of planet upon radius of planet square. No, this is p, 1 minus. We'll write it as rp by 10. So depth. So we will considering uh, the center of mass. So center of mass is at r by 10 depth. So this will be rp. So this cancel. So we will have g mp by rp square into 9 by 10. Now we have to write mp. So we'll write mp as density into volume. Volume will be 4 by 3 pi rp cube divided by rp square into 9 by 10. Now this density of planet will be equal to Earth, so I will just write it as RE. So RP will get cancelled, so this will be RP. Okay. Now let's just solve it. So we have G dash will be G. So density of Earth will be ME upon 4 by 3 pi RE square into RP into 9 by 10. So we'll just 4 by 3, and this was 4 by 3 pi. These will get cancelled. And this is actually G of Earth. So we will have G of Earth into RP. RP was RE by 10. So this was cube. So we will left with one RE. Okay, we'll left with one RE. So this will be RE by 10 into 9 by 10. So 10 will get cancelled, RE get cancelled. So we'll get 9 by 10 as G dash. Now the tension will be M into G dash. Now mass. So the linear mass density is 10 raised to power minus 3 into this. So this is R by RP by 5. So we will write 10 raised to power minus 3 into RP by 5 into G dash was 9 by 10. Now RP was RE by 10, so this will be 50 into 9 by 10. RE, how much, what we have to take? RE we have to take 6 into 10 raised to power 6. Okay, so this is 10 raised to power minus 3 into 6 into 10 raised to power 6 into 9 by 500. So this will be 1000 and this is 2. So it will be 9 into 6, 54 into 2, it will be 108. Is there an option? Yes. So B will be the option. Okay. So 108 Newton, right? So it was easy question, nothing to worry. There is a little bit calculation here, of course. Let's move on to our third question. So a spherically symmetric gravitation system of particles of mass density this, where rho naught is constant, a test mass can undergo circular motion under the influence of gravitational field of particle. Okay, perfect. Its speed v as a function of r from the center of the system is represented by. So we have a spherical mass density. Okay. The test mass can undergo circular motion under the influence of gravitational field. Its speed v as a function of distance. So this is the rho naught is constant. Okay. Now we know the gravitation, if it is going in a circular path, then force on it will be equals to mv square by r, right? Now Fg will be what? M into gravitational field, right? M into gravitational field, and this will be equals to mv square by r, right? R is the distance from it. So let's just take it as small. So this M will get cancelled. So simply v square will be r into Eg. Okay. Now Eg we know. Eg is what? It was Gmr by r cube for r less than greater than 0 less than equals to r, and for r greater than r it was Gm by r square, right? So v square will be, we'll just have to multiply with r, so we'll get Gm r square by r cube for r greater than 0 less than equals to r, and it will be Gm by r, right, for r greater than r. So now, so initially v is proportional to r for r less than greater than 0 less than equals to r, and then v will be inversely proportional to uh, in the root, right? So it will be a parabol, right? So it will be a no, so this will be a hyperbola itself, right? So these two options will be wrong. We must have some other options. Let me check it. Right. So mm, there were two options more, I think. Uh, yeah. So graph will be like this. Okay, I don't have it. So graph will be, the graph of this will be First it will increase from 0 and then it will decrease something like this, right? And this will be at okay. So there were an option called C. C was the option. Now let's move on to our fourth question. Let's move on to our fourth question. Okay. So what we have here is the magnitude of gravitational field at a distance r1 and r2 from the center of a uniform sphere of radius r, and this is very easy, right? At a distance, if r1 is less than r, right, the magnitude of gravitational field from the center of a uniform sphere of radius r and mass m is f1 and f2. So if r1 is less than r and r2 is less than r, so we know force, the gravitational field was g m r by r cube, so it was proportional. So if both are less than r, then f1 will be proportional to r, right? So f1 by f2, so it will have, so so we will have f1 by f2 will be equals to r1 by r, right? So this will be the option, and this was for r less than r. For r greater than equal to r, we have what was the gravitational field was gm by r square, so inversely proportional. So if both were greater, okay, so if both were greater, then f1 will be proportional to f will be proportional to 1 by r square. So we will have f1 by f2 will be equal to r2 square by r1 square. So B will be the option, right? So this was extremely easy question. So A and B will be the option. Let's move on to this next question we have, right? So imagine a light planet revolving around a very massive star in a circular orbit of radius r. Okay, so we have a star here, and this is the planet revolving. The radius of the orbit is r, and time period is t, right? Okay. The gravitational force of attraction between the planet and the star is proportional to this. So we have given Fg is proportional to r to the power minus 5 by 2. So we'll write Fg is equals to k r to the power minus 5 by 2. And this Fg will be equals to mv square by r, right? Mv square by r. So we have v square will be equals to k r to the power 1 minus 5 by 2 will be k r to the power, so this k by m we can write, okay, to the power minus 3 by 2. So this is our v square, right? This is our v square. Now if I want to find the time period, so time period was 2 pi r by v, and we have to find t square is proportional to it. So let's square them. So this is some constant. Let's write it c, and r square, and v square, this is some constant. So this was constant, and let's just put it here, minus 3 by 2. So we have c r 2 plus 3 by 2. This minus 3 by 2 will go up and it will become positive. So we have c r to the power 4 plus 3, 7 by 2. Right? So we have these. Okay. So again, it was very simple, nothing to worry here. Let's move on to our sixth question. Okay. So in this, a large spherical mass m is fixed at one position and two identical point masses, this and this, are kept on a line passing through m, seen figure. The point mass is connected by a rod. So this is a rod here of length L, and this assembly is free to move along the connecting. All the three masses interact only through their mutual gravitational interaction, right? When the point mass is near to m, so this is 3L. Tension in the rod is 0. Okay. So we have to use free way to make free body diagram. So this, let's say this is 1, this is 2. So on this first particle, the force will be here, this will be F due to small m, and here the force will be due to capital M. So we'll write it as on 1. Okay. Now maybe it has some acceleration here. Let's just say A. And there will be tension also. So tension will be in this direction. For 2, for 2, small f will be here, capital F. The force due to capital due to this capital M will be Fm2, and the tension will be in this direction also, and acceleration will be in this direction. So both will have same acceleration because this is not a string, this is a rod. Now the tension we have to put it 0, so we'll just write it as Fm1 minus Fm will be equal to m into A. So tension I'm just making it 0 here, and here we'll have Fm2 plus Fm will be equals to m into A, right? So we have to find m. So A must we must eliminate A. So let's just subtract it. So this will get cancelled. This will be Fm1 minus Fm2, and this will be minus 2Fm is equals to 0, right? So let's just find. So Fm1 will be, this is 3L, right? So it will be Gmm by 3L whole square minus Fm2 will be 3L plus L, it's 4L. So it will be Gmm upon 4L whole square minus 2. And the force between these two masses will be simply Gmm upon L square, right? Equals to 0. So G small m, G small m, G small m will get cancelled. So this is what, m by 9. So L square also get cancelled. M by 16 equals to 2m, right? L square I have eliminated already. So we have 16 minus 9, 7m upon 16 into 9 equals to 2 small m. So we have m as 7m upon 16 into 9. So 16 into 9 will be, yes, 144, right? It will be 144. So if I multiply by 2, we'll have 14m by 288. So k will be 14, right? K will be 14, right? Oh, okay, okay. 2 we have to divide. So we don't need to multiply it actually. Yes, we don't need to multiply it actually. So we'll have simply 7m by 288. So k will be 7. Okay. So it was easy question. Let's move on to our seventh question. Let's move on to our seventh question. So we have three particles. Okay. Each of mass m are situated at a vertices of an equilateral triangle of length a. Okay, perfect. Mm, The only forces acting on the particle are their mutual. Okay. It is desired that each particle moves in a circle while maintaining the original mutual separation A. Okay. So we have a circular path, right? And we have these three particles like this, right? So we have these three particles. Let me just rub this. This just represents the path and the distances. Okay. Now we have this is our first particle, this is our second, and this is our third particle, right? And this will be the center of this circle. So this is just the center of the circle, right? Now this is A. Okay. So find the initial velocity given. So that also find the time period. So look, if this has a velocity v and this will be the radius. Okay. Now we must know this whole distance, this distance, right? You should remember this always. So this distance is how much? Look, this is a by 2 and this is a. So this distance turn out to be root 3 by 2a. Always remember. And the centroid splits into 2 is to 1. So this part, okay, this part, it will be our radius. So radius will be the second part of this. So it will be what? 2 by 3 of this, right? So remember it will be a by root 3. Okay, so it will be a by root 3. So this will get our radius. Now just we have to use our formula. So now look, one more thing. So mb square by r will be here, and look, this particle will be applying a force in this direction, and this will be applying force in this direction. So the resultant will be in this direction, right? So this whole angle is 60. Let's find the resultant first. So f resultant will be root f square plus 2f square cos 60. So it will be root 3f, right? So this root 3f must be equal to mv square by r. So root 3 f will be gm square by distance between them is simply a square equal to mv square by r. R is what? A by root 3. So look, root 3 will get cancelled. One a will get cancelled. One m will get cancelled. So right. So velocity square will be gm by a. So velocity will turn out to be gm by a whole root. Right. Now if I want to find the time period will be 2 pi r upon v. So it will be 2 pi r will be a by root 3 and v is root gm by a. So one this a root 2 and a will get cancelled, so we'll have root a in the numerator. So time period will be 2 pi root a upon 3 gm. Okay, so a upon 3. Okay, so this will go here. Okay, so we'll have a plus 1 by 2. So we'll have a to the power 3 by 2. So this will be q, right? Yeah, so this is in the denominator of the denominator, which becomes numerator, and this is already numerator. So this will be the answer, right? Let's move on to our eighth question. So these are quite easy, right? Let's move on to our right. So we have a simple pendulum of time period t1 when on the surface Earth surface, t2 when it is taken to a height r above the Earth's surface. Okay, so we know time period on the Earth will be 2 pi root r by g, right? So it is t1 and this is g. If it is taken at a height r, so this will be So what will be the formula? Formula will be G upon, yes, it will be the formula was G dash. It was G M by R plus D whole square, right? So G dash will be G M by, so D is R, so it will be 4R square. So we have G by 4, right? G by 4. So next new time period will be 2 pi root R. Now this R was what? This R was, this was, okay, this was length of the pendulum, right? Right? Okay. Now the length is same. New G will come G by 4. So new time period will be 2 times of T1, right? So it will become 2 times of T1. So it will be D, right? 2 pi root L by G. Perfect. Let's move on to our next question. If the radius of Earth were to shrink by 1%, so R will become R minus R into 1 by 100. So it will become 99 by 100 R. Okay, it, its mass is same. The acceleration due to gravity of the Earth. Oh, so this is quite simple, right? Acceleration due to gravity is gm by r square. So if radius is decreased, g will increase. So it will increase. Okay. Next, we have our 10th question right here. Okay. So what we have here is the numerical value of angular velocity of rotation of Earth should be radian per second in order to make the effective acceleration due to gravity at equator equal to 0. So we know g dash was g minus r omega square cos theta, right? Now at equator cos theta will be 90-degree, right? So if theta is 90-degree here, then let's just put it here. So it was r omega cos square theta. Oh, so yeah, so theta will be at equator theta will be 0-degree, right? So at equator theta will be 0-degree, and effective gravity will be 0, so this will become 0. So we have g will be equal to r omega square. So we have to find the omega. Omega will be root g by r. So it will be root 10 divided by, so you can take 9.8, right? The calculation will be better, I think. This will be 6.4 into 10 raised to power 6. No, so this will be, decimal will get cancelled, so it will be 7 root 2 divided by the 64 will be, this will be 10 raised to power 3, and the root of 64 will be 8. Okay, so you have to do the calculation. So we will get 7 into 1.4, this divided by 8. So if you put 1.6, so you will get approximately 1.2 something. Okay, so you will get 1.2 into 10 raised to power minus 3. Okay, let's move on to our next question, 11th. So it was easy, quite easy. You just check the calculation if there was some error. Let's move on to our next question. Right. What we have here is a binary star system consists of two stars A and B, which consist which have time period T and TB. Okay. The radius RA and RB and mass M and B then. Okay. So if they're binary system, let's say this is our first star and this is our second star. Okay. Now, like, look, they will be rotating about their center of mass. Oh, right? So this will be rotating like this, and this will be rotating like this. Okay, right? Okay, perfect. So let's say this was our A, so this will be RA, and it has mass MA. This is MB, and this distance will be RB. Okay. Now the time period will be T and TP. Now we have to check which one is true. Now look, if they are rotating about their center of mass, the omega will be same, right? This will be moving like with the speed of VB. This will be moving with the speed of VA. Okay. Now what will be happening? The force on both the particle will be same. So F will be equals to M VA square by RA. Okay. Or we can write it as M V will be omega R. So it will be omega square A RA, right? Okay. So it will be rotating with the omega into RA, and this is mass M. And this will be equal to MB omega B square RB, right? Now, if we get look, both are equal, right? So this let's say this is FA and this is FB. So we know FA equals to FB because the gravitational force on them will be mutual. So this is same. So if I get some relation between them and we can find omega A, then we'll get if the time period is greater or less or what will be the relation, right? So look, let's say this is our origin and this is the center of mass of the system. So center of mass of the system. Now if this is whole system, the center of mass must be at rest. Okay, and if this is origin, then let's write the coordinate for them. So it will be uh, so how will write? So R of center of mass will be MA plus MB upon MA plus MB, and R of center of mass is 0. So this will simply be MA plus MB equal to 0. So we will have MA will be equal to minus. So negative is saying that one will be in the left, another will be in the right direction. So we'll just write the magnitude. It will be MB. So let's just put this here. So we have MA omega square A equal to MB omega B square. So if this and this is equal, this whole will get cancelled and we'll have omega equal to omega B. So hence time period of A will be equal to time period of B. So this was quite easy, but a little bit tricky. So D will be the option. Let's move on to our 12th question. So we have this, our 12th. If the distance between the Earth and the Sun were half its present value, the number of days in a year would have been. Okay, so we know time period is proportional to RQ by the Kepler's law, right? So what happens is, let's say this was our initial, so T initial, so T initial square upon T final square will be R initial cube upon R final cube, right? So initial was 365, right? So 365 square upon T final square. our initial. Our initial was, let's just put it like this, and final will be half. So it will be r initial cube upon 8, right? So we will have t final square will be 365 square divided by, so 8 will go here and it will be divided by, right? So t final will be simply 365 divided by 2, and this will be root 2, right? So if I use the calculator really fast, so you can solve it manually, of course. So 365, half of 365 will be, it will be 182.5 divided by root 2, and root 2 is 1.4. So this will be less than 182.5. So this will be the answer. Okay, if I use the calculator, let's just find the exact answer. So yes, it will be approximately 130. 129 is the correct option. Yes, let's move on to our 13th question. 13th question, we have the ratio of Earth's orbital angular momentum to its mass is 4.4. So we have the momentum, angular momentum MBR divided by M is what? 4.4 into 10 raised to power 15 meter square upon second, right? Will get cancelled. So we have VR equal to 4.4 into 10 raised to power 15 meter square per second. Now we have to find the area it is enclosed by it. So we have area is what? So let's say in some time t, the angle covered is theta and the length it is covering is L, and this is R. So we know theta is L by R. So area in this time will be pi r square. It will be theta upon 2 pi. So we have r square theta upon 2, right? In this t time. In time t, right? Now this is v. So v is actually L by t. So we write v as L by t. So we'll have L upon t, r will be equal to 4.4 into 10 raised to power 15, right? Now look, this L is what? It is r theta. So let's just put it here. So we have r square theta upon t will be equal to 4.4 into 10 raised to power 15. So let's just put, so this will be our first, this is our second. From these area will get, it will be r square theta will be this. It will be 4.4 into 10 raised to power 15 into t upon 2. Now the earth completes one rotation about sun in 365 days, right? So we'll just write 4.4 into 10 raised to power 15 by 2 into 365 into 24 into 60 into 60. So 60 into 60. This is our meter square. So if you calculate this, you will get approximately 7 into 10 raised to power 1, 2, 3, 4, 5, 6, 7. So I've just used the calculator, so it will be 10 raised to power into 15. So we'll get approximately 7 into 10 raised to power 22 meter square. This will be your answer. This is approximately, of course, approx. Okay, perfect. Let's move on to our 14th question. Let's move on to our 14th question. So what we have here is, according to Kepler's second law, the radius vector of planet R from the sun with equal area in equal interval of time. The law is the consequence of conservation of angular momentum. Okay, so of course, almost all the question, right, of the gravitation, the concept will be using is conservation of energy and conservation of angular momentum. Almost 90% of question will solve like this on these two concepts. So the equal sweeps equal area into equal interval time is based on conservation of angular momentum, and we have just solved the question from that. Let's move on to our next question. So this will be our 15th question, right? So this is our 15th question, right? So what we have here is a thin uniform angular disk of mass m, outer radius is 4r and inner radius is 3r. Okay, so it's this is nothing, there is nothing, just hole, and here is our material. Okay, the work required to take a unit mass from point P to the infinity. So we know the potential at infinity is 0. We consider it. So if we find the potential at a V, then we can simply find the potential energy of this system, and this will be the work, right? So let's just find the potential at P. So how will it find? So we will consider, right? We'll consider a integrating element like this, right? So this will be our integrating element at a distance r, the thickness will be dr. So we know the potential due to disk was, so let's just write dv. Okay, so we will have integration k, right? K means here will be g, the mass is dm upon root x square plus, or we'll say small r square plus, this is 4r, so 4r the whole square, right? Okay, so dm will be what? So it will be m upon the area will be pi 4r square minus 3r square, because the mass is distributed in this area into dr, into 2 pi r 2 pi r here. So let's just put it here. So we'll have g m 2 pi r dr upon, this will be a 16 minus 9, so 7r square, and the root is this r square plus 16r square. So the constants will get, some of the constant will get cancelled and other will take it out. So just let it be. Okay, so let's just v. Okay, I'm not putting any limits here for now. So we have gm 2 upon 7r square, and this will be r dr upon root r square plus 16 capital R square. Okay, now if I say r square plus 16 capital R square will be equals to uh, t square. Okay, so we have 2r dr will be equal to 2t dt. So 2 will get cancelled, so r dr will be t dt. So I'll have t dt upon, this is simply t. This will get, so it will be t, so 2 by 7 g m by r square. So I'm not putting the limit here, I haven't put the limit till now. So this will have v, it will be 2 upon 7 g m by r square, and the dt will be t, and this is t, it will be root r square plus 16 r square, right? So look, now the limits will be putting here. So the radius, this radius is from, now the formula for this is the potential at some point P. So it is just simply Vp, and the limit will be putting from 3R to 4R. So 3R to 4R. So we will have 2 upon 7 gm by r square. If you put 4R, this will be 32. So it will be uh, 16 into 2. So it will be 4r root 2, right? So this will be 4r root 2 minus, if you put 3 here, so it will be 25, because 9. So 3 square will be 9, so it will be 25R, so it will be simply 5R, right? So this is the potential at P. You can take R common and it'll cancel, so it will be simply 2 by 7 Gm by R 4 root 2 minus 5, right? Now the potential energy will be 2 by 7 G, and if it is unit mass, so it will be into 1 upon R 4 root 2 minus 5, and a negative will come, right? So which option will it be? So it will be, so the work done we have to do. So we have, this is the potential energy at point P. So work done will be, we have to do, right? Because the force, gravitational force will be here. So we have to apply a force here. This is due to external, and we have to do the work done. So work done will be the positive. So which option will be correct? A will be correct option. Okay. So it has asked work required. So required work will be the positive. We have to do the work. We have to apply a force against this gravitation. So we have to do work on this particle. So it will be positive, right? So let's move on to our 16th question. Okay. So we have 16th and 17th. Both the questions are here. Yes. So if G, let me stretch it a bit so that it will be visible. Okay. So we have G is the acceleration due to gravity on our surface. The gain in potential energy of the object of mass m raised from surface of Earth to a height equal to radius. Okay. So look, the object is here and then it reaches here. So this is R. Okay. So let's just write the potential energy of the particle here. So UP, U naught, I'll write U naught, or so U initial, let's just write U initial. So U initial. So U initial of the particle will be half minus G small m capital M divided by R. Now here the potential energy, the final potential energy will be G m m by 2R minus, right? So gain will be U final minus U initial. So it will be minus G m capital M by 2R minus minus plus. So G m m by 2R. So R. So we will have G capital M small m upon 2R. And if you multiply it by R, and this is R, so we'll have G m R square. This is small g m R by 2. So this will be the change in potential energy, which will be the gain in the potential energy. So A will be the option. Okay. Let's move on to our 17th question. So what we have here is a solid sphere of uniform density 4 units is located with a center of origin O, the coordinates. Okay. Two sphere of equal radius A with their center this respectively are taken out. Okay. So we have removed this part. Perfect. So the gravitational force due to object at the origin is 0. Yes. So origin it will be 0, right? Because these are symmetrical. So initially it was 0. If you haven't taken out these two spheres, the potential at this point is 0. Now if you remove them, and it will be symmetrical. So if you put negative here and negative mass here, then it will get cancel out each other, and hence it will be 0. So A is correct, right? Next, the gravitational force at a point 2 comma 0 comma 0. So here we want to find the gravitational force. Now let's check. So will it be 0? We have to find. Okay. So look, first we'll consider this as a whole, and it has a mass capital M. right? And it has a density rho. Now what happens is if we removed one sphere from here and one sphere from here, okay, right? So we have removed these two sphere. So let's just say the mass is small m, which will be rho into the volume. It will be 4 by 3 pi r cube. So r is 1. So it will be rho 4 pi 4 pi rho by 3 is this small m. Okay, perfect. Now we have to find the field at point B. Now field at point B will be first due to this whole sphere. So field at point B will be due to whole sphere. So this distance is what? 2r, right? So this distance is 2r. So it will be G capital M upon r cube into 2r. And the radius of the whole sphere is 4. So capital R. So let's just use it. Capital R is 4. So this is 2. So this is 2 units. This is 2 and capital R is 4. So I'll just write here as 4 cube. 4 cube into 2. Okay. Minus look, this negative sphere has no influence at B. Okay, because it is the center. So at the center, the electric field due to this will be 0. So it will be 0. And due to A, it will be, this is 2 and this is 2. So it is total 4. So it will be minus G small m upon 4 square. Right? Okay. So what we'll have? So G upon this is 416 into 4 into 2 minus G. The small m is what? So this is capital M. So rho into 4 by 3 pi upon this is 16. Now capital M is what? So capital M we can write rho into 4 by 3 pi 4 cube, right? It will be 4 cube. Okay. So let's just put it here. So G upon 16 we can take it as common. So we'll have G upon 16. M we can write rho into 4 by 3 pi 4 cube upon 2. 2 was there. Okay. Minus G by 16. Rho 4 by 3 pi. G by 16 we have taken common. So clearly it is non-zero. So B is incorrect. Okay. So at B there will be electric field. It will not get cancelled out due to negative mass. Now, the gravitational potential is same at all points in the circle y square plus z square equal to 36. So look, we have to study this. Now, this is YZ plane, so our sphere will look like this. So this will be our sphere. Okay. Now, if you look here, these A and B are symmetrically placed. Okay. So these are symmetrically placed. So in any circle in this in YZ whose center is origin, the potential will be same. So it will not change. So look, y square plus z square, they have the center at origin. Because of similarity, their potential will be same. Gravitation potential again in y square z square equal to 4, it will be same. Because any circle whose center is origin, because of symmetry, the potential will be same. Okay. If you take another circle like this, let's just take circle like this. Okay. Now look, their center is origin and A and B are symmetrically placed. Okay, so this is the YZ. So we have to visualize this. So A and C are correct. So option will be A, C, D. So this question I will put it in moderate. It's a bit tricky question, but comparatively it is easy, not hard one. Okay, let's move on to our 18th question. So we have 18 and 19. Okay, what we have here is distance between the center of two stars is 10 a. The masses are m and 16m. The radii are a and 2. Okay, so we have one star over here and another star over here. So this is m, radius is a. This is radius is 2a and this is 16m. Okay, the body a body of mass m is fired straight from the surface of the larger star. So let's just say a body has, okay, so let me join this and we'll take this particle here. Okay, so this is it. Now it is shot from here. What should be the minimum initial speed to reach the surface of the smaller? So we have to find the minimum speed. Okay, look, the in between these two spheres there will be a point where the electric field, sorry, gravitational field will be zero, right? After that point, if the particle is here, this will pull it automatically towards itself, right? So we just need to give the velocity such that this particle will reach to a point where the gravitational field is zero. Okay, so let's just first find the gravitational field. So field due to this, let's say this is x. Okay, let's say this is x. Now the distance between them is 10a. So look, this is 2a, this is a, so this will be 7a minus x. Okay, uh, so this will be 7a minus x, right? Now let's find the electric field at p point. So electric field p must be 0. So due to this, now x plus 2a, so it will be g into 16m upon x plus 2a, right? So it will be x plus 2a to the whole square must be equal to, this is a, this is 7a minus x, so it is 8a minus x, right? So it will be g m upon 8a minus x to the whole square. So this will get cancelled, and if you take a root, we'll have 4 upon x plus 2a will be equal to 1 upon 8a minus x. So we have to use plus minus. So just cross multiply them. We'll have 32a minus 4x will be equal to plus minus x plus 2a. Okay, let's take one as plus and another as negative. So if you take plus, we'll have 30a equal to 5x. So x will turn out to be 6a. Okay, now if we take minus, then here will be 3x. This is minus, here will be plus, so it will be 34a equal to this. So x will turn out to be, it will be 11 point something. So look, x cannot be greater than this. So this is not our option because the point should be in the middle. So x equal to 6a will be the correct. Okay. Now we have the situation. Let me make the diagram again. So this is our smaller sphere. This is our bigger sphere. Okay. Now their center are like here. This is the line joining here. And the point P is this. So x is 6a. So this is 6a. This was 2a. And this will be a. And this will be a. Okay. So just we have to make the particle this small m to come at P point. After that, it will automatically be reached to this sphere. Okay. So let's say this is P and this is Q. So we can write energy equation from P to P and Q, right? So total energy at Q will be equal to, uh, look, so total energy at P. Okay. So at Q, the total energy will be half mv square minus the potential energy due to big sphere. It will be minus g into 16m small m upon 2a, and due to big sphere will be, this is 6, 7 and 8, so it will be minus g m small m upon 8. Okay, at P the kinetic energy should be 0 because we just need to make it reach at point P. After that it will automatically go to the smaller sphere. Now the field at P, the potential at P will be, due to smaller sphere, it will be minus g m small m upon, this is a, this is a, so it will be 2a minus, due to this it will be minus g 16m small m upon 6 and 2 8, right? So let's just solve here. What we get, what we get this is half mv square. Okay, so the small m will get cancelled, small m will get cancelled, the small m will get cancelled, and we have v square by 2. This will go here and it will plus, so we have gm will take, so this is 8, so this is 8 and a will take common, so 8 plus, this will be 1 by 8 minus 1 by 2, and this will be minus 2. So we have 6 plus uh, 1 by 8 minus 1 by 2, so 8 will be the LCM. So 8 into 6, it will be 48 plus 1 minus 4. Okay, so v square by 2 equal to gm by, so 49 minus 4, it will be 45 by 8a. So this 2 will get cancelled, so we'll have root, this will be 4. Okay, so we have 45 by 4 gm by a. So I think calculation should be right. This will be our answer, right? So we can take 3 and 2 outside, so we'll be having 9 5 will be inside, so it will be 5 gm by a. So this will be our answer. Okay, it was quite easy question. Now the tricky part was we have to like if you use the potential energy from here to here, the answer will come out to be wrong. This was the tricky part to solve, to understand this. Okay, now let's move on to our last question, which is here itself, 19th question. So what we have here is a particle is projected vertically upward from the surface of the earth with kinetic energy equal to half the minimum value needed for it to escape. Okay, so we have a velocity here, right? Now we know the escape velocity was what? It was root 2gr, right? Okay, so escape velocity was root 2gr, and we have with the kinetic energy equal to half this. So the kinetic energy to escape it, it should be uh, it was like root g m by r, right? So this was escape, the energy escape, the kinetic energy required to escape it. Okay, so we have given the kinetic energy half of this is, let's say this is k naught, so this is k naught by 2, the height to which it is raised. Okay, so let's say it raised like this, and this is h. So we'll write the things here. So let's say this is 1, this is 2. So total energy at 1 will be equal to total energy at 2. Total energy at 1 will be minus g m by r. and this will be plus k naught by 2. So this is k naught. So it will be g m m by 2r will be equal to, the kinetic energy is 0 here, plus minus g m m by h plus r. So this is h plus r. So it will be minus g m m by 2r minus g m m by h plus r. So minus this will get cancelled. So here h will be equal to r, right? So this is easy. So this was our last question. So we have discussed a total of 19 question from all these topic. The next video will be based on escape velocity and satellite, and there will be last 21 question we'll be discussing. Okay. So thank you.